In section 5.1, we'll look at systems of linear equations in two variables. We'll identify solutions to systems, solve systems, and then we'll use systems to answer application problems. So the first question is, what is a system of linear equations? It would be two or more linear equations used together. So anytime you have a system, you're just looking at a couple of equations, maybe more, that they're going to be used together to represent something in some sort of environment or whatever. A solution to a system of linear equations, and since we're just doing two variables right now, we'll go ahead and use the specific definition for two. It's an ordered pair that satisfies all equations in the system. So since there are two variables, the solution will be an ordered pair. When we get to three variables at the end of class, then we'll have an ordered triple. And satisfies all equations, that simply means you could put those values for x and y in all of the equations that you have, and then they would make those equations true. Let's look at example 1. Determine if the point 3, 4 is a solution to the system 5x minus y equals 11 and x plus y equals 7. So to determine if you do have a solution, you just check those values in both equations. And if they're true in both equations, then it is a solution. So x is equal to 3, so I'm going to plug in 3 for x. Y is 4, so I'm going to plug in 4 for y. And we're going to do the is that equal symbol. Remember, you're not allowed to move things over left and right. You just need to evaluate the left, evaluate the right, and see if both sides are equal. 5 times 3 is 15, minus 4 might be equal to 11. 15 minus 4 is 11. So this point checks in the first equation. For it to be a solution to the system, it has to work in all of the equations, so we check it in the other equation as well. So we're going to have 3 plus 4 might be equal to 7, and 7 is equal to 7. So that checks out there. So the answer is yes, 3, 4 is a solution to the system. Let's look at example 2. Determine if the point negative 3, 1 is a solution to the system 2x plus 3y equals negative 3 and x minus 8y equals negative 5. So again, we just check this point. So this would be 2 times negative 3 plus 3 times 1 might be equal to negative 3. That's negative 6 plus 3 might be equal to negative 3. And negative 3 is equal to negative 3. That one checks out. Let's check it in the second equation. So we have negative 3 minus 8 times 1 might be equal to negative 5. This would be negative 3 minus 8 might be equal to negative 5. But this time we have negative 11 and negative 5, and those are not equal. The solution has to satisfy all of the equations. This one fails to satisfy the second one, so no, negative 3, 1 is not a solution to the system. All right, let's take a look at page 2. And we're going to explore 3 different ways to find solutions to systems. The first one is the graphical solutions. So in example 3, we have graphs of these systems, and we want to find their solution. The solution to a system is the intersection of the graphs. So in the first one here on the left, we have the line 2x minus y equals 1 and y equals negative 1/2 x plus 4. Those 2 lines intersect at this point, which is 3, 2. And so the solution is 3, 2. Write that as a set of ordered, 3, 2. 3, 2. 2, 3. My bad. This will go on the blooper reel. 2, 3. Very good. And so there's the solution. Now, when you have a solution, at least one solution, we say that the equations are consistent. And in this case, when you have only one solution, we say that the variables are independent. Independent means that the x has its own answer, not based on the y has its own answer based only on y, not based on the x. You'll see the contrasting example in this next one. All right, in the second one, we have 3x minus y equals 2 and 6x minus 2y equals 4. We've graphed both of those on the grid, and they overlap completely. They are, in fact, the same line. So what would be an ordered pair where they intersect? Well, every ordered pair on that line is an ordered pair that's in the solution. So we're going to use set builder notation. And we're going to say that the solution is the set of points x, y, such that, and then we just have to throw in one of these equations. 3x minus y equals 2. So any point that's on the line 3x minus y equals 2 is going to be a solution. There are infinitely many solutions. Since you have at least one solution, we say that the system is consistent. But the value for x depends on the value for y. That's given by this equation here. So whatever y you want to come up with depends on whatever value of x you want to give it. So the x and the y are dependent on each other. All right, lastly, we have y equals 2/3 x minus 3 and y equals 2/3 x plus 1. Notice that those 2 lines are, in fact, parallel. If you have parallel lines that are not the same line, then they never intersect. So there is no solution. So it's the empty set. No solution. And we say that this system is inconsistent. There is no independent or dependent because you don't have a solution to start with. So it's just inconsistent, and then that's it. All right, let's look at substitution. This is the second method. Example 4, solve the system using substitution. X plus 3y equals 11. and 4x minus y equals 18. So the key to substitution is to solve one of the equations for one of the variables, and then substitute that into the other equation and solve. Okay. So I'm going to start with the top equation, x plus 3y equals 11, and I'm going to solve that for x. When I solve it for x, I get x is equal to 11 minus 3y. Next, I'm going to substitute that into the bottom equation. So we have 4, and then it's x, so I'm going to substitute what I know x is equal to, which is 11 minus 3y. Then minus y equals 18. Now notice that I now have an equation that has one single variable in it. When you get to that step, then you can solve for that equation. So distribute. You get 44 minus 12y minus y equals 18. Negative 12y minus y is negative 13y. 18 minus 44 is negative 26. Divide both sides by negative 13 and you get y equals 2. So that's half of the solution. Then to find the other half, you do what we call back substituting. And so x is now equal to 11 minus 3 times y, but we know that the y is 2. And you get x equals 5. So the solution is the point 5, 2. All right, let's look at the addition method. Solve the system using addition. 3x plus 7y equals negative 1, and negative 3x plus 4y equals negative 10. So the trick to the addition method is to line up the variables in columns. So here's the x's, here are the y's, here are the numbers. You may have to rearrange some of the elements of the equation in order to get things to work out. But do you see how you have positive 3x on the first equation and negative 3x on the second equation? You can simply take these equations and add them straight down. So 3x minus 3x is 0. I won't write anything for that. 7y plus 4y is 11y. And negative 1 minus 10 is negative 11. So in the addition method, some people call this addition elimination, whatever. You add down the equations to create a new equation. That equation that is generated is also consistent with the entire system. So you can't get out of the system just by adding equations together. So we can solve this, and we get negative 1. And then you just substitute that new value, y equals negative 1, into one of the equations, your choice, and you solve for x. So I'll put it into the first one here. So 3x plus 7 times negative 1 equals negative 1. 3x minus 7 equals negative 1. Move the 7 to the other side. It goes over as a positive. And x is equal to 2. So the solution set is the point 2, negative 1. Okay, let's look at example 6. Solve the system using addition. So first I'm going to rewrite this. I have to move the y's to the left side. When they come over as a negative. And then line everything up, so x's and y's and the constants. Now in the first example on this page, we were lucky. We had 3x and we had negative 3x, and so you just add and they canceled. Okay, you're not going to get that fortunate every time. We're going to have to create some equations that work here. So what I'm going to do is I'm going to plan to get rid of the y's. So the question is, what number could I multiply by the first one to create some constant, some coefficient of the y? And then I could also come back and multiply the second equation by some other constant. What could I multiply each of those by to create y's that would then cancel? And sometimes you can pick smaller numbers, but what will always work is if you just cross up the coefficients. There's a 5 on that one, so I'm going to multiply this equation by a 5. There's a 7 on that one, I'm going to multiply that one by a 7. You may need to throw in a negative to get them to be opposites. These are already opposites, so I'll just use these positive versions here. So what do we get? So you're going to multiply 5 by everything there. So that's going to be 70x minus 35y equals 30. And we're going to multiply the bottom equation by 7. It's going to be 21x plus 35y equals 35. Now you have created two equations that have opposite coefficients on the y, so when you add them, they will cancel. 70x and 21x is 91x. The y's cancel, and that leaves us with 65. Divide both sides by 91, and you get x is equal to 5/7. 65 and 91 are multiples of 13, so cancel off 13s and you get 5/7. Now come back and back substitute. I'm going to substitute into the bottom equation. So 3x plus 5y equals 5. The x is now 5/7. So we have 3 times 5/7 plus 5y equals 5. I don't like working with fractions, so I'm going to multiply everything by 7. The 7 is going to distribute to all of these. The 7 cancels with the 7 in the denominator on the first one, but it multiplies on the y. So we get 15, that's the 3 and the 5, plus 35y equals 35. Move the 15 over, you get 20. Divide both sides by 35, and we get y equals 4/7. So this gives me the solution 5/7, 4/7. All right, let's take a look at page 4. Solve this system, and you can use any method that you'd like. So y equals 3x minus 5 and 6x minus 2y equals 10. This one looks geared up and ready for substitution because we have y equals stuff already. So I'm going to substitute this equation into the bottom equation. So 6x minus 2 times 3x minus 5 equals 10. Solve this equation. So we get 6x minus 6x plus 10 equals 10. and the x's cancel, and we get 10 equals 10, or if you want to subtract 10s, you get 0 equals 0, whatever you want to do. Either way, this equation is true. When you have an equation that is true, that means it works for all x. Now, because we're in a system with two variables, that doesn't mean it works for all x and all y, right? It means that we can use any x, but then the y is based on the x that we choose. So, any x, and then that x goes into one of these equations, and you produce the y. So the solution is the set of ordered pairs, x comma y, such that y is equal to 3x minus 5. So essentially what happened was these two equations were the same line when you graph them. So they overlap everywhere that they're on the line, and so only the ordered pairs that are on the line are solutions. We would say that this is consistent and dependent. All right, let's look at example 8. Solve 8x minus 4y equals 7 and negative 2x plus y equals 9. I'm going to use an addition method here. This here. All right. I'm going to multiply the bottom equation by 4 and create a new equation there. So the top equation stays the same. It's 8x minus 4y equals 7. That one is the same. The bottom equation, let's multiply that by 4. So 4 times negative 2 is negative 8x. So I'm setting it up here to cancel the x's. Looks good. 4 times y is plus 4y. Uh-oh, that doesn't look so good, does it? And then 4 times 9 is 36. So here I'm trying to cancel off the x's. 8x minus 8x is 0. So that's good. But then, what else happened? Negative 4x and positive 4x was also 0. So in my attempt to get rid of only the x's, I also got rid of the y's. That's no good. What is this, 43? 0 plus 0 equals 43. True or false? That is false. So there is no solution. And this equation, or this system rather, is inconsistent. So this was an example of two parallel lines that do not intersect. All right, let's look at page 5. Example 9. A boat is traveling upstream against the current. It takes 2 hours to travel 36 miles. On the return trip downstream with the current, it only takes an hour and a half. What is the speed of the boat in still water, and what is the speed of the current? So let's set up some variables. Let's let x be equal to the boat speed. And let's let y be the speed of the current. From there, let's set up a table. So we're going to have distance, rate, and time. For my rows, let's have upstream and downstream. First of all, we know the distance. The distance is 36 miles, upstream and downstream. We know the times. Upstream was 2 hours, downstream was an hour and a half. find the rates for upstream and downstream. You have to think about this and then turn it into an algebraic expression. If the boat is going to travel at X miles per hour or whatever, but then the current is working against it when it's going upstream, then you just subtract off that rate. So the rate, the actual rate that the boat was going, or the actual, average rate, is X minus Y. But that's because the boat was working against the current. Now, when the boat returns, the current is going the same direction as the boat. So the current helps the boat. And so if the boat was going X, then it gets the benefit of the current. So the rate that it goes downstream is X plus Y. All right, let's turn that into a system. So remember that rate is equal to, or distance rather, is equal to rate times time. So distance equals rate times time. And distance is equal to rate times time. So we get the system 36 is equal to X minus Y times 2. And 36 is equal to X plus Y times 1.5. Let's distribute the numbers. So we're going to get 36 is equal to 2x minus 2y. And 36 is equal to 1.5x plus 1.5y. Let me use an addition method. I see I have opposite signs on the y, so those are going to be the easiest ones to get rid of. I'm just going to multiply by the other coefficients. So to get rid of the y, I'm going to need to multiply the first one by 1.5 and the second one by 2. So 1.5 times 36 is 54. 1.5 times 2 is 3, so that's 3x, and then 3y, minus 3y. Let's multiply the bottom one by 2, so 36 times 2 is 72. 1.5 times 2 is 3. 1.5 times 2 is 3. So we're in good shape this time. The y's are opposites of each other. So we can take these two equations, add them down, and cancel the y's. So negative 3y plus 3y is 0, so that's gone. But here we have 6x and 126. Divide both sides by 6, and you get x is equal to 21. Back substitute x equals 21 into one of these equations here. I'll choose the first one. And we get 36 is equal to 21 minus y times 2. Instead of distributing, go ahead and divide both sides by 2. So you get 18 is equal to 21 minus y. Subtract the 21, and you get negative 3 is equal to negative y. And y equals 3. Now we won't write this one as an ordered pair because it's asking for actual information. So the boat speed was 21 miles per hour, and the current was 3 miles per hour.